Ladies and gentlemen, we are very lucky today to have with us Sanjiv Singh from Carnegie Mellon University. I know Sanjiv for about 30 years now. When I met him this morning, he told me, le plus ça change, le plus c'est la même chose, which is, it's French for the more things change, the more they stay the same. You know, 30 years ago, I was an assistant professor, and he was a graduate student at CMU, and we were both interested in active perception. And 30 years later, we are both interested in active perception.
There you go.
But Sanjiv, in the meantime, he has become the CEO of Near Earth Autonomy, a multi-million-dollar company at CMU that is devoted to automation in the drone service sector, agriculture, and a variety of problems regarding this. Sanjiv is one of the world's authorities on perception for real-world systems. He has led several multi-million-dollar projects. Notably, in 2010, he led a big consortium for demonstrating for the first time takeoff and landing autonomously of helicopters. He is also a consulting professor at Carnegie Mellon University, and today he is going to speak to us about an autonomy stack for air vehicles, which is a topic very close to our heart, because in my lab we are working on a similar problem for very small drones. So we are very happy to have Sanjiv today.
Thank you. Thank you. Thank you. It's great to be here. I was here a number of years ago. This place looks completely different, so congratulations on that. By way of introduction, I should say I feel like I'm a recovering academic. So, you know, sometimes I fall off the wagon and I still have to go do these kinds of things. But I love it. I love to think about ideas. The recent work we've been thinking about doing is things that are not only good ideas, but they also have practical applications. Sometimes they're done best outside the exact university setting, but I still live right on the edge of campus and spend quite a bit of time at the university. So let me get started. I wanted to give you a kind of a vision of the future. This kind of looks like something out of Blade Runner. But, you know, what you see here, of course, they're the traditional aircraft that are flying high. But then, you know, these kinds of aircraft, they'll fly off the top of a building onto another building. And, you know, some things that are carrying things at a low altitude, some larger vehicles that will take off in these urban settings. And this is not a concept from Wired magazine or some futuristic thing like this. This is actually a vision that NASA put out. So NASA is thinking, you know, the A side of NASA, the air side, not the space side, is thinking that this is the vision of the future of how aircraft are going to have to fly in urban environments. So it's a kind of a interesting area to think about. And if you have this vision, then what is it going to take to actually accomplish this? And today I'm going to talk to you about some of this. Now, just as a dose of reality, in 1924, there was this idea that in 20 years we would have flying autos. So the idea was that, you know, we just started the era of the automobile. So how far could the aeromobile be? Not too far. And the idea was, consider what such a machine will mean to the man who works in the city. He could live several miles further away from the heart of the city and spend less time getting to and from work. So 1924, they had this idea, right? So the thought here is that if we've been thinking about this for a while, and it's getting a little bit more and more real over the years, where are we going to look to make the technology that will enable the flying auto the future. So one place we might look is the ground vehicle world, which maybe some of you are familiar with. I'm familiar with this vehicle because in 1985, when I got my master's, before I was a grad student, I went to Carnegie Mellon to work on that vehicle, and I arrived 2 weeks before this big blue van showed up. And that first rack was my rack. And that was a whole rack was filled with stuff to make automate this. There was the steering wheel, and then there was the hydrostatic transmission, and that was the rack I worked on. A couple of things to note. Back then, cameras were big broadcast quality cameras. They were the only cameras you could digitize. And then there was this box about that big, like a big industrial oven. That was the scanning laser rangefinder, one of a kind, made by a company called Aram. It was 128 by 30 pixel scanning laser rangefinder, 1 per 1 hertz. Okay, so in about 1 year, it took us to get this thing to move at walking speed up this little narrow path right next to campus. And I was right there when I was taking the baby steps. So that was a world. And then fast forward almost a decade, cameras have gotten like small cans, like they look like a Coke can about this size. And then, but the laser scanner is just still huge. Another 12 years go by and the DARPA Urban Challenge happened. I was pretty involved in that. And you have all kinds of sensors, radar in the front, all kinds of LiDAR. First time this spinning laser scanner put out 1 million points per second. All kinds of very interesting things came together. Almost took like 20 years to the point where you could actually show something happening, right? And then this is Google embedding just what's necessary, driving at highway speeds. Now, if you're in Pittsburgh, there are 5 self-driving car companies testing every day, trying to get cars to drive by themselves. It's kind of amusing, as a roboticist to pull up next to them. I'm trying to figure out if they're really in auto mode and what can I do to make the life difficult, but not get too crazy. Trying to conduct my own experiment, right? But it's a real kick, actually, to be in one of these little streets and see a self-driving car right next to you. So I think, it must be that people have figured out that either the cost of living in Pittsburgh is so low and there's all these talented people there, or that if you can get cars to work in Pittsburgh, they'll work anywhere else. We have like the worst driving conditions, the narrow streets, the faded lines, the potholes, and, up and down, lots of elevation changes. So in any case, we're not complaining. So if you look and see, what is it that autonomy, where is the autonomy, right? Very informally. Now, this is very informally. Just give me some poetic license here. It's in these sensors in the front. They're what make these vehicles aware of the environment, and then somewhere in the back there's computing, and so the eyes and the brain are roughly what makes this thing autonomy. Of course, the mechanism is a very important part, but we want to think about, if you want to do this with air vehicles, we'll be thinking about similar kinds of things. So let's think about, in these kinds of things, all the problems we have to solve, right? These are the kinds of problems we want to solve. Often these are different people who work on them, like some sort of ego motion, very robust ego motion, what's around me, some way of figuring out the space to objects in the world and what they are. Sometimes you need to first classify them and then to predict what they're going to do in the near future so that you can avoid them. Failure detection is to figure out if something's going wrong, something's unexpected, and doing something different based on that. Planning, which is to how do you get to the goal given all of this. If I'm failing or some things around me or based on where I am, how do I guide the vehicle to the goal? And then how do I improve in teaming? How do you cooperate to do more, right? So these are the problems that we've been working on. Unfortunately, this is a sort of truth in advertising from lessons. Mostly what we do is we really work on these problems, right? Where am I and what's around me? The rest of it, we've got lots of graduate students. They'll start the tape again, and we'll do this. We'll learn some things over here. And of course, the bar keeps getting lower and lower, or higher and higher, whatever your metric is, for these kinds of things. And I'll talk about sort of how do you push the limits there in this area here. But these are the kinds of problems we'll solve. And what you'll see is that many of them are also problems we have to solve. They've got a slightly different flavor to them. We often don't have to do that much classification for air vehicles because we want to stay away from everything. You have to figure out, is that vegetation or is that wooden kind of thing? Because if it's vegetation, I can get closer, but if it's something that's dense, then I might have a crash. So you don't have to figure that out. You don't have to figure out, is that a bicyclist or a pedestrian? For a self-driving car, that's very important. A cyclist and a pedestrian move very differently, so you have to classify them so you can predict what they're going to do so you can avoid them. Some of these problems get easier in the air side, but there's familiar kinds of things. So first thing first, I had a kind of a dream project, which was to actually work on a flying car, okay? And this was a DARPA project. They're actually building a flying car. So I wrote a proposal to see if we could do this. And here's a scenario, right? Just happen to be driving around the coast in your Humvee, and the road ahead is blocked for some reason. And then, you've got this interface in your car. You're actually trying to get to the other side of this little island you're on. And no, this is not a big deal, right? You can actually generate a route. But then what happens next is only what you dream about when you're stuck on the 495. Right? I mean, I'm sure every one of you has dreamt this, right? At this kind of thing that will just go. But underneath the hood is a very familiar representation, probabilistic representation that can help a vehicle get information, keep it over time, do it efficiently such that the computation doesn't blow up, and then guide itself. You have to think about different things. The dynamics of these vehicles matters a lot. So they were actually, the funny thing about this program is that we were working with two companies that were developing different concepts. So as a kind of a joke, before we got their CAD models, we showed a Humvee flying, and they thought, okay, this is great, we'll do this. We'll just stick with the Humvee. So we called it Chitty Chitty Bang Bang. And the rest of it was, we've actually built a simulator in which you could sit in the simulator and you have an out-of-the-world view. It's a very realistic kind of a simulator. There's actual steering wheel. You could make the commands. And then what we showed was, for this DARPA program, how all the computing could happen in real time and how would the user interface work. So you've got somebody who's not a trained pilot. What they're doing is there's some conversation going on between this operator, not a pilot. They don't have different steering mechanisms, different control mechanisms for the car versus the flying part. And what it's been told to land somewhere, but there's something there. So the sensors on board are going to say, no, that's not a good place to land, and will not let it land until it finds a good place. So here, it's coming in along this glide path. It finds a safe place, and then the operator can see that that circle is turned green, and the operator presses land and lands. Okay, so this is sort of first step in a concept. Great DARPA project that went on to become what's known as the Ares project. And I don't know if some of you might know Ashish Bagai was faculty in aerospace for a while here. He, or I don't know exactly what his designation was, very closely aligned with UMD, but then he led this program for a while at DARPA. Okay, but, all right, so that was sim, right? Sim is sim. We say simulation is doomed to success. That's our problem. So we want to look at what would you do, like if you had to do this in real life. And what I want to show you is two scales. At this scale, this is, it's called the unmanned little bird, but it's not really little. The rotor diameter is 30 feet, 10 meters. So the rotor would be maybe about the size of this room, okay? So just the rotor alone. So it's a decent sized thing. It's like the Ford Mustang of helicopters, very fast, very agile kind of helicopter, a little temperamental. So maybe not the Ford Mustang, maybe the Alfa Romeo, right, of helicopters. And so what we did was same thing, right? Sensors in the front and then computing. the back. Now, fortunately, small things fly slowly, right? So you don't have to look out that far. So we could do the same thing with sensors today at the smaller scale. So we can, I'll talk about here. So what's different here to there is you can buy your way out of some of these tough problems. You fly high, there's not much there. You have to take care about the first 50 feet and the last 50 feet. And at this scale, you can fly fast, and you can get the best of everything. You can get the best laser you could buy, the best positioning system you can have. So you can sort of intellectually cheat. You know, as roboticists, the idea is that you could get such good components that somehow or the other feels like cheating. I think Yanis would agree. You know, you can't just buy your way out of it. He's in this thing. We want to do it on this. A deck of cards has to fly, right? So that scale. Otherwise, he's not happy, right? So he wants to make artificial flies or something like this, insects. So, okay, this is the best I can do. Here, you want to fly fast. You want to fly very close to things. You're going to solve a lot of these problems. So I'm going to talk to you about both of these problems, both ends of these problems. First, I'll talk to you about where you can actually cheat, and then we'll say, okay, not quite, it didn't happen quite in that order, but let's take it that way. It'll make more sense that way, not chronologically. Okay, so here's my definition of what aerial autonomy means. So you're going to do aerial autonomy. Let's boil it down. No jargon, okay? There will be no discussion of deep learning in this talk. Some of you will be relieved. Some of you will be sad. But I say aerial autonomy is about flying safe, landing safe, doing it without GPS, even when things go wrong. Okay, so I can't get it any less jargony than that. Another way to say it is, you know, sense, plan, interact. Sense, plan, act, interact. Should be obvious to anybody who thinks about these kinds of things in our world. For the aerospace people think about flight control as the inner loop, and then it's the outer loop on top of the inner loop. Right? So that's what air autonomy is about. Another way to think about it is dealing with all the things that can go wrong, all the things that are not expected, all the things that are not in the nominal case, the off-nominal conditions. Okay, so that's what autonomy is. Still very informally. Let's take this idea of what can we do? Can we take things from the ground and use it in the air? So here's a Cirrus helicopter. But what we've done is right in the back here, we've taken a sensor that's really built for the automotive world and put it on there. Okay, it puts out 700,000 points here. Now it's not 700,000 points per second. You can make 700,000 points every second. Every point is taken from a slightly different place because it's making a range measurement in time of flight. So the trick is really how do you register this, right? So we're going to put this on a Cirrus helicopter, and let's see what we can do with that. So, you know, some sort of like simple registration, right? And the idea is if you want to have these vehicles fly close to things, then you have to have this kind of awareness all around. So here's, again, Cirrus helicopter. This is a little bit bigger than the unmanned little bird. This is a newsjapper scale helicopter. What you see here is just by registering the data, okay, in real time from that one sensor, at least a vehicle can be quite aware of what the shape of the world is around it. So this is very low tech, okay? Low tech, simple, low tech in the sense not easy to do, but this is very good positioning that you get if you have enough money. And then you're able to, with good timing, be able to register each of these 700,000 points per second at the right time, make it correspond to the position and velocity, and be able to create that kind of registration. Okay, so that's a simple thing. But now let's look at what you could do with it, because that doesn't give you autonomy. That just gives you some sort of awareness of the shape of the world. We want to do something more. So here's sort of like the capstone we did in this large project for the ONR, which is fly a helicopter into that site, come in at a glide slope 3 degrees without any map of the area, no hover, no overflight, and decide if there's a good place to land, and if there is land there. Okay, so here it is. It's coming in and builds this point cloud. As it's coming in at 100 knots in this shallow glide slope, 3-degree glide slope means that the landing zone is like a fraction of a degree at some distance at a kilometer, and as it comes in, you have to sort of scan that area, build that point cloud, then classify all the places that are landable and land. Okay? So again, if you've got enough money, enough engineers to sort of build a stabilized point gimbal to point this, and you have enough time and have enough time to sort of enough computing in the back to do all the classification, you can do this. Okay, a big problem that we have is flying without GPS. And the problem is that currently the high-end systems will drift. So if you get a 1 degree or 2 degree an hour IMU, then GPS goes away, is jammed or degraded or something, then your position will drift at 1 to 2 degrees an hour. Maybe worse sometimes in some cases. That's a kind of an average case. And so we wanted to show what's possible with this not crazy submarine grade IMU, but this $40,000 IMU. You know, just a bargain, really, right? You can go to you can go to Best Buy and pick it up. Except you have to show all your bona fides that you're not going to put it on a missile to pick up this this IMU. So we decided. I asked our flight ops people. I said, "Here's Pittsburgh. There's a place over here called Zelienople." I said, "I want you to fly from Allentown to Zelienople." And they said, "No, that's not going to work. It's too far. How about Ashtabula to Zanesville?" You might get this idea. There's a theme there. What we were looking for. So fly long distance from A to Z, some town, real towns. These are actual towns. And they got 140 miles from here to there, flying over all kinds of places with this high-end system with a LiDAR looking down. And so what can you do? Take off, no GPS, and how far can you get? So with an IMU, just this, what we call tactical grade IMU, not nav grade, flew 140 miles, you're off by about 30 miles. And then with your favorite VO algorithm attached to the IMU, you can get about 2 miles away. And then if you have LiDAR, you can do some sort of LiDAR version of what a Tomahawk does, which is basically get your fix from a terrain map. This is not anything special. This is what's available. You can go to the USGS and pick up 10-meter DEM, which is every 10 meters you have an elevation. Vegetation is removed, houses are removed, somehow or the other they do is filtering, they get this is publicly available elevation map. You have that, and then you have a LiDAR, and of course you have to do some processing because you're going to sense the trees, you're going to sense the houses, fly over rivers where there'll be no reflections, etc. But okay, we can get 260 feet away. So if you have this high-end system, you can do well. Your things are good. If you have a couple $1 million to spare, we can fly into very complex sites, do the thing that we do with autonomous cars today, land safely. We can fly without GPS, very long distances, take off to landing without any GPS. There's a question here?
So you're comparing against a known map, a 3D map of the ground?
Yeah, we have this extremely high-end system also. We can run it in RTK, DGPS mode, and we know also where the location we landed because we surveyed. So then you locate, you say, where did the vehicle think it landed? And it landed here for sure. It thought we were over here, right? With the IMU alone. Yeah.
What if it is raining, snowing, or there is fog or smoke?
So, okay, in the worst of conditions, it doesn't work. We can talk about this a lot. We went to Yuma, Arizona, where they create these brownout situations and looked and saw that the LiDAR that we use is a special LiDAR. It's an aerial LiDAR. It's called full waveform analysis, so you don't get the first return or the last return, you get every return. Okay, so you can do analysis of that. You can look at the last return, usually from an opaque object. Sometimes the last return is not from an opaque object, so then you have to do some filtering, but it can actually get rid of a lot of the obscurance. Mild rain or even moderate rain is also not a problem. In this particular case, the configuration is downward looking, so you're good. I mean, just the system itself is protected, and you get some squirrel things here, but thank goodness for ransack, right? Ransack is great. See, I worked with the guy from SRI who developed Ransack, and only later, after I worked with him for a long time, I found out he's the guy who wrote Ransack. I was like, what? Mr. Ransack? He's just a normal guy. You know, it's like, without Ransack, where would we be? So Ransack helps a lot, but of course in the worst condition then. If it's zero, what we call 0, 0, meaning at 0 feet you see 0, right? Then you're dead. That's what happened to Kobe Bryant, you know. Then, yeah, we can talk about how insects would do in 0, 0. Okay. All right. So that's if you cheat a lot, right? Cheat meaning you have lots of money. Yes.
LiDAR is giving you 700,000 points per second, and you're processing it all in real time. Basically, control of that.
So these are slightly different things, right? I mean, 700,000 points per second was that Velodyne, that spinning Velodyne here. This is an aerial survey LiDAR that looks straight down. This produces about 250 to 350,000 points. We could actually get close to 500,000 points because it's not flying that far high. When you fly on a helicopter, you fly a few hundred feet. You're not flying 50 feet. You're not flying at 5,000 feet. You fly at a few hundred feet off the ground. And so when you fly at a few hundred feet, you can actually have a higher pulse rate. You get about 500,000 points per second. What we're doing here is we're actually estimating the state. We flew this thing manually from here to there and then estimated, in this case, what would the state be? What did the state estimation system be under all these different paradigms? Okay?
So the data from the LiDAR was processed in real time?
Yeah, everything is processed in real time. Everything is done in real time. Yeah, so this is one of the things, there's the vision mafia who believe that LiDAR is just, you're about to go to hell. So you somehow or the other, you've done a carnal sin if you've done LiDAR. But, okay, so I'm here, I'm guilty as charged. I'm ready for going wherever I need to go. And I will tell you how LiDAR is used, in real time. Very small processors, okay? Vision actually turns out to have a whole lot more bandwidth. If you think about it, you get a megabyte or megapixel, 30 frames per second. The amount of data coming out of a LiDAR actually is 1 order or 2 orders of magnitude less. Okay? All right, so if we cheat just a little less, okay, we say, okay, well, we don't have a $1 million computer. We only have a system that's, 2 orders of magnitude less than that, multi-million-dollar things. And LiDAR is not 200,000, but it's only 4,000. So this is using, something that most of you might have seen. This is a Velodyne LiDAR. It's 400 grams, 600 grams, and puts out 280,000 points per second. Just a quad-core processor here. This is like a shoebox, okay? It has a decent IMU GPS. So we're still sort of in this kind of cheating paradigm because we're going to solve the navigation problem separately. We're going to try to put that into some sort of process. We'll solve the navigation problem separately. We'll find shape from the navigation problem, and then we'll try to do something with it. Okay, and so, well, it doesn't work too badly. Now you're sort of like, come down, and here's the kind of thing you could do. Okay, similar kind. This is a sort of a larger quad rotor than you would have seen. It would carry about 30 kilos. Okay, so maybe 6 feet wide or so, and similar kinds of things. It's told fly somewhere. That place is not good to land on. It develops this this shape, understanding. This is all happening in real time. This is fully autonomous, and landing. This is just visualization, and there it is landing. This is completely push buttons. You push the button, it flies somewhere, and it lands there. So, same idea. A couple of iterations of this. We can think about what we might do with this. We could put it on different kinds of aircraft. So here we are. This is a very interesting aircraft. It's called hybrid VTOL. It's got wings and rotors. So rotors to take off and land, and they can fly. This is, the Army wants to deliver blood, whole blood, a few hundred miles. They want to carry just a few packets of blood. They want to go a long distance, but they want to land. They want to parachute the blood down. So same idea. This comes in, and while it's flying in at low speeds, it can evaluate the thing and then come down and land. Okay, so that's another variation. Here's a second variation. This is now flying onto a ship, actually pretty close to here, recovering to a ship deck on the Chesapeake. This is like a year and a half ago. This is not autonomous, but it's fully instrumented and it's got all this ground truthing going on in there. But now what we do is we add a whole bunch of other sensors to be able to show what else we could do. So you got thermal. You could find the ship is a hot blob on a cold sea, so you could find it from some distance and track it. We could use small radios that can actually provide range. So these are small radios you get range from, and you can get some localization information. It's not very well conditioned, right? It's all coming from one range information from a very narrow angle. So, but it's a difficult localization problem. Then you can use beacons. Now, how we ground truth this, one way, easy, is that we estimate the relative pose to the deck, and then we paint that green pattern onto the deck. If we get it exactly right, then then you're correct. Now, I lied about deep learning. We snuck in some deep learning when I wasn't looking. So it's like, okay, that's a boat. All right, fine. A boat detector. It's my favorite thing to rail about, you know. It's a cheap shot, but okay. So we could use LiDAR too. Okay, again, we're still cheating, right? Are we cheating here? No, we're not cheating fully because we're actually getting relative pose and using that navigation to actually register the LiDAR data. We're not doing what we usually do, which is solve this with IMU, GPS, and then use that to register the data. Actually, that's just a terrible way to do things because GPS is good. We all have gotten addicted to it. It's like worse than heroin. Withdrawal is bad, okay? The problem is that GPS is supposed to tell you when it's not working, but often it just lies. So when it says that it's got good confidence, often it doesn't have a good solution, right? So this is a problem, right? We can't even really trust it. And we'll get into this, how do you know about error models in a few minutes, but that's another thing that I'm eager to think about. Oh, so we are in the right place. So what if we stop cheating, all right? So we say, all right, we want to solve all of these problems. And we want to do this in all kinds of constraints I'll talk to you about. But here's a reason why. You might be flying above a river under a canopy. You know, everybody does that, right? But you might be have a robot that's inside a deep mine, or, you know, your dog might happen to be robotic and it's running through the forest with you. Where is it going to get GPS? So we have to solve this. In fact, you got to solve this with all sorts of other things. It's got to deal with fast rotations. It's got to be real time, low drift, low latency, high frequency, smooth, lightweight. And by the way, can you do it for $500? So tall order. But we've got to do this, right? This is what's going to make Yanis happy. So we stop cheating, right? We're not going to solve these two things. We've got to do this. So here's what we want. So this is not, this is what we did, and then I'll tell you why this is noteworthy. So here's a little aircraft. This is like a smaller aircraft than I saw in the TOPS lab, the DJI-100. It takes off here and lands there. And by the time it lands there, it starts off with no map. It has this kind of representation. So what you want is you want this representation of the environment. You want it in real time. You want to do this. You want to also solve for this. You want to solve for the state, 6DOF state, or maybe 12DOF state, and you want to do it on board, right? So it's a DJI 100. Then how do you do this? How is this even going to work? And it has to be small, and we'll talk about expense in a little bit. All right, so here's where it gets interesting. This is my favorite slide. So this is my way of thinking about what a Kalman filter does. Kalman filter is like a meat grinder, right? This is how we solve problems. So the idea is, it's like it makes sausage. Right? And the idea is you put in whatever you want, and you crank the thing, and then some more sausage comes out. So that sausage, might have some IMU and some visual feature, a laser landmark, whatever. It's going into the sausage, and you crank it, right? That's how it happens, right? It's all no memory. That's what the common thing is, only just one. There's a basic fundamental thing that we, as roboticists, fool ourselves into. Maybe the aerospace guys got us on this. It's all the aerospace guys' fault, right? They got us thinking about that when we take measurements, we can really actually have a sensible error model, okay? And so here's how we do it. We get some data, we get some ground truth, and we say, it's okay, look at that. There's a bell curve in here somewhere. No, it's not zero mean. Let's just make it a bell curve, and surely if you throw it in a MATLAB, you will get a model, and yes, of course, we will put it in there. But the point is that that's complete garbage. For lots of times, this is the part we skip over. Where did you get the error model for? Well, I took data and I put it into my thing, and well, what does the error distribution look like? Well, it kind of looks like nothing, right? So your basic common assumption is violated, right? Right? But we pretend it's not, and we do this anyway, right? The common assumption is not violated, and we say, okay, well, yeah, one at a time. It doesn't matter which order it comes in. Look, it runs, and most of the time it works. But the problem is the common assumption is not. So no wonder we get shitty results in this kind of stuff. Especially, what is the error distribution of taking a range measurement? No, not the error model is not very well defined at all. Okay, it varies on the surface normal, on the material that you're looking at. So no way this is going to work, right? But we pretend it does. We make it work. Make the graph, get the video, and you're done. There's another neat way, which is I call the cocktail shaker method, right? So you take all the things in here, you put it in the cocktail shaker, you shake it. Sometimes you can do it really fast. Shake it, pour it, shake it, pour it, okay? But it's useless too, right? I mean, it all matters. It's all depending on this kind of thing. Maybe get a little bit better because you're not so dependent on the outliers. Filter out the outliers with the cocktail shaker. But okay, if you shake it for a long time, maybe for a few days, you might get a thing. But then the buzz is gone. It's time to go home anyway. So no point drinking there. So here's a new way, okay, to do this. And this is, I'm going to show you, I don't know if this is going to make sense, is we stop believing that the Kalman filter, okay? Stop believing that the Kalman filter is the way to do it. And there's a very, very obvious and easy way to think about it, which is that these things, you shouldn't be putting all these measurements together at the same time. You get some inertial measurement, you use that estimate to sort of cue your visual odometry, that you use that thing here to cue your laser odometry, and even to solve an ICP problem. Now, nobody thought about using ICP, right? Except one grad student who I said, forget about this. This is never going to work. And he said, no, let me do it. And then he came back and I said, what loop closure did you use? And he said, I didn't use a loop closure method. I said, what? That doesn't make any sense. How did you do this? So we sat for like 6 months. I wouldn't let him propose his thesis till he actually figured out why it was working. And what he was doing was I actually honestly thought, this is being taped, you might watch it, that he was just fabricating this stuff, and that's when you know when you're not fabricating, and he's doing it over and over again. I'll show you the video, that there's something here. So nobody thought about an ICP problem where you're almost right. You're solving like the very last part of it, right? ICP problems are like the thing that come out of the structure for motion community. They said, okay, well, give me pictures of the Colosseum in any order, and I will give you a 3D model, right? This is what the vision community wants. I don't want any sequences. Forget about IMU or anything else like that. So you solve this problem from any starting condition. No wonder it gives you crappy results, right? most of the time. There's some brilliant people who've got this figured out on the vision side. But you know, the idea here is if you could do this, if you could really solve, you're almost there. Your bowl of conversion is very tight, then you could do this in real time. Okay, so here's the video. Right? So I told G, who was working on this, I said, you know, he was running around inside the building. I said, well, you got to do something more than this. So he created this sort of ninja grad student video. How am I doing this? No. I think I can run it. Yeah. So he put the laser scanner on his head, right? Because we didn't have enough money to do this. And so this is the laser you're getting, right? Hopeless. He's got this computing in his backpack. But, okay, you got an IMU, really crappy IMU. And now you run this IMU to do visual. There's actually not even any visual odometry here. And then in real time, you can do this, right? So this is 2015. So he said, okay, all right, you can propose your thesis. So, you know, G's done an amazing job, and I'm just taking credit for his work. So he got better at this over time, spun off a company, was still a grad student, and then he came back to propose his thesis, defend his thesis. So here he is. He's got a little bit better version of this, but still just in a 1 kilo case. He's got the LiDAR. Now he doesn't have it strapped to his head. Just walking around in real time, you're building this map. So this is about 300,000 points per second. IMU camera, right? And this is just normal. So you can do this. You can do this thing from the ground, but of course we're not done yet, right? So want to do this from the air also. And now without any pre-processing or whatever else, you can fly the vehicle, and it's got the same thing, and it just locks onto that model. It doesn't care if it saw these things 3 seconds ago or 1 hour ago or 3 weeks ago. It locks on. You have to be close for this ICP. The time where you stop to where you start up again, that takes just a little bit of thing on its own. It finds that match, and then you know you can lock on. You solve this basically 3D SLAM problem. And this is no post-processing. You're done. All right, so actually, it said before you graduate, you have to solve this one other problem. You know, you try to get the best out of the grad students here. It said, all right, I've been watching, you know, think about this. Everybody's seen this movie, right? This now seems so dated. So this is our thing, right? Forget about mapping. All right, mapping and 3D SLAM. You got to solve this problem. Can we do it? So, of course, he goes off and he comes back and has this video, which is, sure enough, the thing is flying, no map, flying through a forest. You know, question about whether you can, and sure enough, there happen to be some stormtroopers right there. Where is it? Stormtroopers are hiding. See. So it's told, go in that direction. It's localizing itself. It's creating a map, and then it's avoiding these things. I don't know why it's not playing here. I'll show you some more. So, there it is. Always seems to get stuck here. All right, let me show you what's under the hood here. This is some first-person view from the heli as it's flying. It's actually doing the same thing. This is just another run like that. And then what it's doing is it's got this forward model of what's possible, all the paths that are dynamically feasible, and is able to, in real time, localize, map, and prune this tree of a few hundred options such that it stays safe. Yes?
Since how fast is the real time here? Like how frequently do you update your map and...
Don't I know you? Yes. No. How fast is flying 10 meters per second?
How fast is the updates of maps and...
As I showed before in that little thing here, inertial at 200 hertz, visual odometry at about 20 hertz, the LiDAR mapping at about 1 hertz.
Sensing part, right? So you have to process that and you have to update.
Right. So you've got a map. I mean, you can make a decision probably. Maybe you were talking about what's the control cycle? Roughly about between 10 and 20 hertz. Yeah. Beyond 20 hertz, you hit some sort of natural frequency of the vehicle. You can't even really react to that. Okay. And then at the end of that, when it's actually done that, of course, what you see is you've got this nice metric map. Okay. Well, so next stage. What if you don't have, if you want to go and build a map, but you want to build it completely and since you have no map, you can't tell the vehicle where to go. And what we saw before was it could localize, it could map, it could even avoid objects. But how do you build a complete map of an area? We call that exploration. This is that same building where we flew around and be able to build this 3D model from the ground and from the air. This is a particularly difficult place. No GPS really actually would work over here. So there's a garage here. We let the vehicle loose out of the garage and say, go out that way. And then you're bound by half a kilometer by half a kilometer thing. Come back when you have either no holes in your map or you've covered, you can't go any further beyond in that area. So this thing is real early results. I can only quantitatively or qualitatively describe it. Here it is. This is a ground vehicle now, and just to simplify, but the blue box doesn't know it's on a ground vehicle. It thinks it's flying. So what it's doing is actually doing an efficient version of what's known as the frontier method, which is you keep these frontiers around, and then you go and search these frontiers and try to explore the frontier there. So what you've got here at the bottom is extremely good localization, okay? Very good mapping, so these maps aren't shadowed, the maps are coherent. If you have in this very unstructured world, I mean, there's nothing there. We didn't add anything. The quality of the localization and mapping keeps it from getting stuck. Now, what happens if you don't solve that localization problem and the mapping problem is that the vehicle often gets stuck in these kind of cul-de-sacs. It doesn't know what to do, not because it can't get out of there, but its perception is fuzzy enough that it can get trapped because the data are misregistered. So you get into this problem of how much data do you want to save and how much do you want to act with. But if you did this thing really well on the front end, this thing works beautifully. And what you see is 20 minutes later, you have this complete map of the area. Okay, so this will just flip into a view, and then I'll try to summarize. So this is completely autonomous. Start here inside the lab, and we were told go this far, and beyond that, if you didn't do the estimation correctly, you wouldn't even be able to set that bound properly. But comes back, and 20 minutes later. So what we know now, we've done some informal estimation comparisons, is it's about 5 to 10 times better than the state-of-the-art in exploration. And this is the kind of stuff that DARPA has a challenge right now. It's called a sub-T challenge. These kinds of algorithms are being used in that sub-T challenge. Okay, I think I'm running out of time, so let me try to recap and have some time for questions, hopefully. So, okay, this is a simplified view of the world. When I think about really complex things, I was talking to Yannis when he came pick me up. I was like, hey, that thing we talked about language being used to understand natural scenes, I'm still thinking about that. So I haven't gotten there yet, okay? This is like, you have to go sit at the feet of the Shiva and learn. But okay, I'm making my way over there. Meanwhile, we have some things that work. So at the very core, we have this localized map thing, essentially 3D SLAM. Then this very fast forward model for staying safe, which encodes the dynamics even at high speeds in very, very complex environments. And you can get to the goal. with very simple methods, if you can have that abstraction, if you have this coherent metric representation, which was never, we could never even really imagine this, that we could have such consistent metric representation. So you could start out with nothing and get this, such that you don't have to play these games. And then, a very efficient way to do exploration is basically a clever data structure that keeps track such that the complexity doesn't increase over time. As you get more and more data, the complexity is constant. That's what helps it over exploration. The problem with exploration is you play this sort of Faustian game. You get lots of detail, and then you get bogged down with the detail, right? So here we have something that, by doing this exploration very efficiently, the complexity is constant as the vehicle goes. Okay, let me say one other thing. Just come back to autonomous flying. These days, I spend a lot of my time not doing writing papers or developing new ideas. I'm trying to think about the business of autonomous flying. All the things we could do practically. So I would be remiss by not telling you why this is so hard, right? I think gravity is really not your friend when you fly, and this is very obvious to us, right? I mean, gravity is just a hard thing to deal with. So what we really need is quantum gravity. So in case anybody is working on quantum gravity here, maybe some physicists in the audience, please, that's what we really need to make this thing happen. I think, we're still using E&M. We're forcing air over wings to get lift, and that's only going to be so much. I'm looking over there, the aerospace guys. You know anybody working on quantum gravity? Please let us know. That's what we really need. So the other part of this is that the airspace game, or flying things, carrying packages, carrying people autonomously, you really have to mitigate for this very rare and dangerous events. And what you need to do is to really do this, you have to push these systems to their limit, and that's very hard to do, right? In ground vehicles, you might be able to build a fenced-in area where you test these things at some high speeds, all the conditions you want. Air vehicles, they get away. No walls matter. It's very hard. And if you want to do them at scale, you might be able to do them small scale inside a building, but at full scale, very, very hard to sort of like test these things, pushing them to the limit. It's possible, but very expensive, very difficult. The final thing here is that, you hear as an engineer, faster, cheaper, better, pick two. The problem here is we need very reliable, very capable, and then very affordable systems, right? We need all three of them. And that means that these systems don't start to work till they all work. It doesn't work till it all works, right? That's what makes this thing hard. But okay, if you're in for it for a life's work, it's not such a bad thing to work on. Okay, so the obligatory slide. Near Earth is now 75 people. It was a small company that started off, spun off from Carnegie Mellon. We actually get a lot of resumes from Maryland, so I was really happy to come here. Somehow or the other, we get all kinds of people applying from here, and you should if you are in this business. So I'll take some questions now. Hopefully I haven't run over my time. Yeah?
So it almost feels like when you saw that LiDAR, right? So
What's it?
What's not solid?
I just told you.
Yeah, but from a research point of view, like you don't have infinite resources, right? Like a company. So you don't have 30 engineers working on this. What would you research that?
I have the problem. We're having dinner or something like that, because I was going to tell you the problem. The hard problem, the really hard problem.
Okay.
Are you going somewhere?
No. I'm
Okay.
here to give you a gift.
Look at that.
T-shirt from our lab
Perfect.
with art behind, with
Yes.
robots.
That's great. That's great. Thank you.
You have
Thank
to
you.
wait till May.
Okay. Oh, no. Okay. Not with global
We are
warming.
very grateful for
Okay.
your talk. Any questions for?
I get it. I'll answer that question. So here's the. There are some specific problems, and here's what it is. Okay, I think you just take one problem, okay? The problem that people want solved the most, which is stable flight, stable navigation in the national airspace. Obviously, if these are commercial systems, you can't carry $1 million system. You can carry a $4,000 laser, but the problem is that as soon as you start flying out of range of that laser, the laser is no good, right? Or you're flying over a cornfield or whatever, so there's no features there, or you're flying high enough. The problem here is how to use vision, because cameras are cheap, we got the computation now, to solve this navigation problem. So this is an open challenge that I think that, and the idea here, I have this idea, fly 100 kilometers with a $100 component and drift no more than 1 meter, okay? So this is a concrete kind of a measured problem that you can think about, okay? Yeah, you could fly 100 kilometers. I showed you 200 kilometers, 140 miles, and have low drift rates. Even at low altitudes with a LiDAR, you can do it. But nationally, LiDAR is not going to be possible, or you'll have to carry a much more expensive and heavy LiDAR, and that doesn't work either. So the idea is here is, it could be there are some variations of this problem, but this is a kind of an open problem, one open problem that I know about. The other problem, of course, semantics always matter. If you can semantically understand the scene, this is, if we want to think about how to do really complex problems, complex things, semantics will matter. If you can solve the nav problem, lots of practical applications become possible.
There are a lot of work in the field of autonomous landing where teaming is there. So are you, from a business point of view, also looking at that?
I'm not sure what you mean. I haven't seen this work. Like, how does teaming help you land?
As in, you have a ground vehicle on which you land. So in that sort of scenario, so the ground vehicle is...
You don't have to be a ground vehicle, right? It could be a pattern.
Yeah.
It could be. So, of course, anytime you can do that, you should do that. I mean, I have a video of recognizing a visual marker or a beacon, like on the ship. On the ship deck, there were all kinds of things. There was a radio, there was a ranging radio, there was a visual pattern of the ship deck markings, there were these IR beacons. So anytime you could put infrastructure to solve your problem, yeah, you should. That's a complete no-brainer to do it. The question is to be able to do this. So you've got this Amazon drone that's going to bring whatever to you, right? Your cleats, because your dog ate your shoes. If you haven't seen that Amazon commercial. So it's flying, and what happens if some critical component fails? It's not going to land on a pattern when it flies over somebody's neighborhood, right? So from that perspective, you have to be able to do the safe landing without, you have to be prepared to do that without something. Yeah. Aviation is all about safety. Very high levels of, very long number of nines at the end to be able to fly over people. And the problem is there's a kind of a pull in the opposite direction. These things, these new vehicles are very popular because they're cheap. But in aviation, safety is completely correlated with cost. So if I had this thing that brought your delivered tomato sauce or whatever else people order, I ordered chickpeas from Amazon and crushed tomatoes, all these, bringing this stuff to me, to my house, if it cost $1 million, that's not going to work, right? So that's what I mean. It has to be capable, it has to be reliable, and then it has to be low cost, right? So how we're going to do that? Well, we're going to replace what, we have a hope of doing this if we replace what the human does there, uses all the reasoning and everything else like that to figure out all these very rare events, right? Yes?
Besides the fact that one case where you had deep learning look at the ship, it seems like everything else was using classical.
Yeah, I told you we snuck in the deep learning. I was trying not to do any.
So what is the aversion to using learning for these kinds of problems?
Very good question. So the learning per se is not bad, right? So I was very keen to do learning as a grad student, and I actually worked with Andrew Moore. He was he's just a new professor Carnegie Mellon when I was finishing my thesis. He was on my thesis committee, and I was learning. I was very keen to think about how to do learning. What he was learning was doing this thing called memory-based learning, which is some way of doing interpolation, right, in a model-less way. And what I was doing was I was trying to find the difference between the model and the experimental data. I was trying to learn that difference that couldn't be modeled. Some first-order model and then try to do that. But at least you have a basis, something that gets the first-order thing. My worry with learning, so that gives me my bona fides on learning. I really want to do learning. The problem with deep learning is you're not sure what it is that the thing is learning. If you try to learn a picture of a artillery tank, is it learned that something about a tank, or is it learned that some shade of green? And you don't know that, and you have no way of inspecting it, right? You don't know what it's learned. You can't introspect. The system cannot introspect to tell you why it learned that. This is another thing I think, learning is not bad. Learning is actually the thing. But what we need, if we need this autonomous system to be certifiable, or you want to be trusted anyway, forget about certifiable. If you want to be trusted, you have to be able to query the system to be able to figure out what it learned. And our current systems basically do interpolation among all the data set. We have no idea what they learn. And it only works as long as you show it another one of those. So if you have face recognition, or let's say road recognition, like find the road, and I put up a picture, hold up a Coke can, it's going to find the road in the Coke can image. It doesn't know that that thing is a Coke can, right? So that's my problem. I mean, I think in very restricted domains it works, but it's become the I don't know. I'm trying to choose my words carefully. Who knows who's working on what?
That's because I saw it was a NASA talk, and he was talking about planning, and he also was like, we don't want to do learning because we don't trust it. So it's a similar.
No. Learning is perfectly fine. There are lots of methods where you can learn some things. You can actually wrap things around. The question is, you have to be very careful to make sure that it has learned what you're supposed to learn, right? If you're learning the delta in between a first-order system and you're trying to get that nonlinear kind of thing and that difference in there, well, that's great. So there's a kind of a debate going on with people who do this kind of robotic learning as to should you learn the delta between the functions or should you learn the function directly? There's an actual real debate there. And then beyond that, what do you do when to say that, hey, that thing doesn't even belong in my set? That is, it's kind of like GPS. GPS will always give you some answer. If it gets multipath, it might not know it's getting multipath, right? It says it's very certain. Same thing, you might have an answer this thing will give you, but you're not assured that it's that confident about its answer. Yeah.
Please.
So initially you mentioned that it's important to know when the system is failing, right? And you gave an example of GPS says that it's giving you a good reading, which it might not be true, right? But with your system, let's say one of your components is failing.
Yeah.
And you detected that one of the components is giving you bad readings at any point.
The answer is depends. We're not. I can't actually tell you truly that we're able to tell some. So one of the reasons why it doesn't matter that much is because we don't have that much dependence on these systems, and there are easier ways to detect whether it's failing. Where if the output of the system is something that you couldn't introspect on, and that would matter a lot, I think that that would be a problem. Okay, but it's a good question, and that's a problem. We are working on taking certain systems and making them certifiable. So the one nice thing about the aerospace world is it has a process of certifying some things. Now, anything non-deterministic is not in that process, not certifiable, but deterministic things can be certified through a certain process. Okay, and when you go through that process, you say that subcomponent, when it's going to fail. You know all the failure modes. It's a very systematic approach. You have a failure tree, and you can say with high certainty that that's a thing, right? I don't know if you take it to the extremes if it would always work, but for some of our capabilities, there is a path to doing that.
So all the tests that you ran, they were like in ideal environment when there was no failing of any point, right?
Yes. We are taking one subsystem, and we're putting it through this DO-178 process, and it's a long way to go. Yeah. Yes.
So far, do you have to worry about any adversaries, or I have a delivery or somebody else is trying to take away?
No. I work for the military. You know. No adversaries. Then you know. There's actually kind of another interesting thing. So you know, if you look at the military use case, they say, well, we've got to carry meals and water and provisions we need to do this, and we want to build these systems such that there's some acceptable failure rate, okay? And so adversary may be okay, you know, that's the kind of thing. Now if you put that in the national airspace, if you think about commercial thing, you'd never be able to say that, because you have to, even if it's, you know, if it's carrying tens of pounds, 50 pounds, it still has to have very high level of reliability. So one of the reliability things would be, you know, people were messing with it. You know, it does the right thing. Adversaries are very advanced. Maybe we'll need deep learning for that. Yes?
So the stack destination model that you showed for odometry?
Yeah.
So you're not doing any sort of loop closure things like in...
You can do loop closure at the end, okay? So if you could look this up, there's a benchmark called KITTI, K-I-T-T-I. Right. So this method is, for many years, it was the top method on that benchmark. So if you look, I mean, they're numbers because they give you data sets you downloaded. And our system's actually now better than that benchmark because that benchmark doesn't have certain kinds of things that we add, right? So our rough statistic number is like this. If you go in the worst case, what's the worst case for one of the systems? You just go like this, right? Basically, there's no turning around, right? If you are moving around in an area, no map, you see things that you've seen just a few seconds ago or a few minutes ago, let's say half a kilometer area, half a kilometer by half a kilometer, you really often don't have to do anything, okay? Now, the worst case is you're going to go that way, right? What happens there is there's no real way because it's doing loop closure basically at every step, right? But then you don't see things you've seen before because there is some drift, right? And the drift we see is about 0.25% of distance travel. It's about 5 times better than most other methods. Most methods are between 1% and 2% of distance travel in the worst case. So in the worst case, if you take a very long loop, or you drive a long loop of 20 kilometers and come back, you'll be off because you won't be able to see the things. And then you can use loop closure for mapping purposes. You want a really good map, you can do all of that loop closure.
But those results were not using. I mean
there was nothing I showed used loop closure.
Right.
Yes.
So any of the maps we saw were quantitative metric distances and how far everything was. Have you thought at all about less structured mapping techniques, say ordinal depth, or techniques that don't require a precise measurement?
Yeah. I'm going to answer this question and take a step back. When I first went to Carnegie Mellon, there was a guy, Hans Berliner, and he was a grandmaster chess player. This is going to be a little bit of a metaphor here. So he was a grandmaster chess player, and he had these graduate students who were like trying to learn how to play chess, or trying to teach these computers how to play chess, right? And they did pretty well. You know, they were modeling on how humans did it. You know, humans don't have search. They don't use search. And then some of his graduate students said, screw that. We're just going to make these computers that look 8 steps ahead. And that became Deep Blue that beat Garry Kasparov, and that became Watson. That group moved over to IBM, Watson, and then they created, they actually did Deep Blue, at deep did not stand for deep learning. I want you to know. Okay, this was way before. We just called them neural nets at that time. Okay, but the thought here is that I don't know why you're asking this, but my thought is we're already at 500 grams. All the people I spoke to who don't like lasers say, they're too heavy, they're too expensive. Well, what's too expensive? What's too heavy, right? If you're, if you're trying to build an insect, yeah, probably too heavy, right? Then yeah, you have to do it, and I respect that. Yeah, we have to by necessity. You can't carry. We don't know of a method here to do laser ranging here at that speed. But we're not trying. We're not getting anything exotic here. I called all the stuff that was exotic. I called it cheating, and now we're looking at Intel NUC. Small processor, few $1,000 LiDAR, a MEMS IMU, and a CMOS camera. So what's wrong with that? No instance of wheel in nature. We use wheels very effectively.
One short question. What's the hobbyist all-in cost for one drone that has this sort of thing? Like, if you're not able to come work for the company, or if you're working on something different but want to play with this stuff, what are you in for? Like $10,000, $15,000?
No. At this, they're still built by hand, but they will be there at some point. There's nothing in there that's high cost, right? I mean, you still have to build in these things and maintain them and train people how to use them, et cetera. Drones, cost a few $1,000s. The system itself is like $50,000 in quantity one at a very low stage right now. I mean, I think the idea here is that this is one of the things I have to bend my mind is how do you make money? How do you how do you not go broke? So, yeah, not quite there, but it's not 2 orders of magnitude away. Questions? Yes.
Are you also looking into alternative designs for UAVs? I mostly saw helicopters or quadcopters. So maybe fixed-wing UAVs or maybe some unconventional that maybe you're working on.
So, I'm a newbie. I've only been spending 15 years in aerospace, right? You have to kind of it's like if you want to be a gymnast, you better start age 5, right? So I'm sorry I missed that time. I'm not designing aircraft right now. So I work with the aircraft that people bring to me. So right now the big nothing against the fixed wing aircraft. The thing about fixed wing aircraft, you have wings, you have rotors on them. Then the thing about there's actually a more serious answer to that. Fixed wing aircraft take off from airports and land at some landing strip, right? Fixed, prepared surface, just because that's just how it flies. Or you launch them out of a catapult and you have to land them. Some way of doing that. That usually these aircraft fly high, okay? So we still so far called near Earth autonomy. Maybe we'll be not really that close, not really that near Earth autonomy. And then then we'd be looking at that. This is an area. One of the reasons I talked about ground vehicles is we brought this whole technology from ground vehicle space into the air vehicle side, right? And that all sort of is very relevant to this when the vehicle is able to sense the environment, or it has to sense the environment, not just able to, it has to sense the environment. When your fixed wing aircraft fly high. Now there are some crazy aircraft that fixed wing, but they fly low, very low. I don't quite know the motivation for those.
Not necessarily fixed wing, but say you have to basically build a flying car. There will be a lot of maneuverability problems too, right?
So the flying cars are usually all VTOL, right? Okay. They're necessarily VTOL. We don't care whether they're tilt rotor or they're ducted fans or they're one rotor or N rotors. I have no preference. The thing is that they should be. So we are trying to be aircraft agnostic. That's our way of looking at it. Is that if it flies a particular kind of profile, then we're interested.
Well, when we with many thanks to Lockheed Martin for sponsoring the seminar, and many thanks to my friend for a beautiful talk.
I hope you liked it.
Thank you very much.